I'm going to talk about the steel-free multi-girder hybrid deck system, mainly the design consideration and construction challenges. So before I start, I would like also to acknowledge the collaborators of this research, that Dr. Ayman Al-Mahdi, who did his PhD on this topic, and Dr. Donna Chen also did her master and PhD on this topic. So we started in 2005. And then Professor Naji Shraif, who co-supervised Ayman Al-Mahdi during his PhD. So a brief overview about what I'll be presenting today. The why hybrid members, and then I'm going to talk about the goals, and then this list talk about the system, the material we use, the optimization, and some safety aspect, the proposed design of the system, and some construction. I won't give detail about the experimental testing, but what in general we have done. So what's going to come up in this presentation is that I'm going to talk about the system itself, that we call it the steel-free bridge hybrid tech system. What's unique about this design, and what were the goals during the stages of this research. More detailed step-by-step description of the structural elements of the system, and the construction of the prototype, quarter-scale prototype system, and what were the problems we faced before and during. And so now, why hybrid members? Dr. Badri mentioned something about this. I will complement a little bit this about that. Because of the research interest in this high-performance material has increased tremendously, primarily due to their high strength-weight ratio, as well as the long-term property. And there is a wide variety of structural design and dimension with strategic arrangement of the material in the cross-section. And it can be cost-effective and potentially competitive to other conventional systems when carefully designed. I'm going to talk about this later. So what were the goals initially when we started in 2005? That because the primary research here focus was how can we prevent the corrosion and long-term maintenance problem that are commonly observed in the conventional bridge construction system. And this ended up to the design of a hybrid system by looking at how we can do it with using optimization in regard to two important things: the economic feasibility and the structural practicality of the system. The design methodology, because here we're going to look at using high-performance material, 4 different materials, and because the material, most of the material are linear elastic behavior, so how we can include safety consideration into the design using the pseudo-ductility behavior. At the end, we wanted to achieve comparable design behavior and performance to the conventional bridge design. Financial feasibility will be achieved, or was achieved, by counterbalancing the higher initial cost with the lower future maintenance expenses. And because the structure can only as strong as its weakest component, so the design here, the utmost importance was to determine the maximum performance as well the structural limit of each individual component of the system. So before we came out to this prototype system, we did that test on the individual components themselves. So what were the material we used here? The fiber-reinforced polymer, the pultruded hollow block GFRP sections, that's a figure shows. We used the carbon FRP sheets unidirectional to supplement the reinforcement at the bottom. We used pultruded GFRP threaded rod. This represents the shear stud for bonding the concrete to the box as well. We use it in the prototype system as a transverse composite action system. The concrete was ultra-high performance concrete, so without any passive internal reinforcement, just a short internal steel fibers, and we cast the concrete on the top of the box girder. So the design methodology, this is how we started the system, that we looked at the component of the girder individual. We have the concrete at the top, the box, we have a carbon fiber sheet at the bottom bonded with the epoxy. We did several tests on this component, and then I talked about optimization and what are the pros and cons of using high-performance material. We know the pros are higher strength, durability, the resistant to environmental factors. The cons were the higher cost, the availability of the material, and member selection. Sometimes you are limited by what's available. So as a designer, our role is to find an economical balance, as I mentioned earlier, cost versus performance. So in terms of the safety, as a designer, you should take care of or have some early warning sign prior to failure. Definitely we don't design for a failure, but in case, we need to design for the ultimate, and we need to have some early warning failure. And this is by providing also adequate sustained load resistance for a period after the impeding failure. So warnings such as excessive deflection, although they might not be desired, visible cracks and discoloration due to corrosion of the internal reinforcement in just normal structure, and audible sound. So this is actually a proposal of the system. I'm going to talk about this in more detail. This composite system, and particular attention was devoted later on to the transverse system in order to be able to have distribution of the load among the girders, which are shown in blue, and then so the system can perform all together as one system. So the area of concern when we started to do the test on the beam itself individually, not as a system, we had the brittle failure. Again, as I mentioned, all this material, they have linear elastic behavior. The ultra high performance concrete, this concrete is about 180 megapascals, so it's almost linear. The buckling of the box, that's the GFRP box, at high load concentration, debonding between the concrete at the top and the GFRP top flange. And then when we thought about doing the system, okay, how can we ensure that you have composite action between the adjacent girder? So I'm going to go over this area of concern, brittle failure. We talked about catastrophic and sudden failure of the structural system. The solution was to incorporate progressive failure mechanism obtained by automation, including the pseudoductility behavior that was based on selecting the material based on the ultimate strain and dimensioning the cross-section to obtain what's the desired sequence in progressive failure. We have concrete at the top, we have the GFRP, we have the CFRP at the bottom. In terms of buckling of the GFRP beam, which we can see on the left-hand side, how we can see this buckling and then rupture. So we thought about cast-in-place UHPC infill inside the box. Now, how we did this, we had to insert styrofoam inside at its several intervals and then make a hole at the top, which will come in the construction later on, and then that's how we filled it with concrete. As well to have the end block at the end with concrete. For the debonding, the loss of the composite action, we investigated different methods of how the concrete at the top can be bonded perfectly to the top flange of the GFRP, and eventually we found that the best is to have epoxy bond coarse silica sand, as you can see here. And then also we had some post-tensioning vertical GFRP bars at the location along the length of this girder. For the transverse composite action, the problem how to ensure all the girders perform collectively and how the load is distributed effectively among in the direction. So the solution was to adopt the transverse system. We use post-tension transverse horizontal strap and rod at regular intervals, and then also we have diaphragms composed of cross bracing. We can see them in the photo here, and this will come in more detail. So how we did the design, this is just to refresh the memory how the system at the end looks, and then I'm going to go over to the area of concern I talked about. So I mentioned about the pseudoductility is by carefully selecting the material based on the strain, and at the end we needed to have the progressive failure that we wanted to design that have rupture of the sheet at the bottom and then followed by the failure of the GFRP box and crashing of the concrete. So we investigated the bond method and behavior at the interface. So on the left-hand side, that's how we tested earlier beams. And then later on, you can see there is nothing. So the shear stud were inserted in the top flange into the concrete. So this even didn't work. So we ended up moving to the mechanical anchors at this location. Okay, so the post-tension vertical GFRP rod at the different locations along the length of the girder. So that's how we have them placed. And that's provide also shear resistance as well pull-out resistance. The transfer direction, we have, this is the proposed system. So as you can see, we have the cross bracing in red, and we have at the top and bottom, we have also GFRP strap at the top and at the bottom, which I will talk about why we need this. So the cross bracing to provide load transfer between the adjacent girders, and the horizontal strap, which is the one at the top, and this is required in design of when you have a very thin slab. The slab here was about 45 millimeters, so it's less than 2 inches. And this has to be as close as we can to the concrete slab. This is without any pre-stressing, just a strap like that. We adopted the word strap as it is in the Canadian code. The bottom rod is the one that is post-tensioned, and this is located as much as you can to the near bottom of the box girder. So at the end, we achieved what we needed in terms of composite action, and then how the load will be transferred into the direction. Again, I want to mention that there's no direct design method for this kind of bridges, so we relied on what we have in the Canadian High Bridge Design Code, especially for the transverse spacing of the girder, and then the design of the diaphragm and design of the transverse straps using the GFRP. In terms of comparison between whether you have okay, let me say something. The weight of an individual girder with the GFRP box, the concrete at the top, the carbon at the bottom, is about 1/4 the weight of as if we designed the entire section with the concrete. So this also gives you an idea about the comparison between reinforced concrete and the system. And the design of the system was done in a way that the neutral axis is at the location between the concrete and the top flange, because we don't need any concrete below the neutral axis. Okay, so the concrete was in full compression. The tensile force was taken by the carbon fiber sheet at the bottom. The GFRP box helped in the shear, and then we have the transverse GFRP rod. So this is the longitudinal view of the 3-meter prototype girder. You can see those infilled concrete, and you can see the GFRP vertical rod and so on. Okay, so that's the system under testing, and that's bottom view. And we can see those bolts here, and everything is GFRP, including the bolt for the transverse top and bottom straps. So the construction, this shows the girders. And you can see in the middle figure behind those rebar, we can see the styrofoam, because we needed to have this spacing in between. And then we insert those GFRP box rod. And we had holes made at every location where we have this concrete to be filled in. And this is called the silica sand, and then another side view. And this is the system altogether. Okay, another view of the system. Okay, I don't know. It's getting slow here. Casting the concrete or mixing the concrete. This is the casting. We use the UHPC. This is very high performance material. And now we face some problems. I'm going to talk about this. And do I have time? Oh, okay. Okay, so the problems we faced were, actually, I'm going to mention them here. The installation of the unbonded GFRP rod. So this was achieved with the PEX sleeve inserted in a pre-drilled hole through the GFRP beam before the installation of the rod. So the issue faced steepage of the epoxy for bonding the carbon, as well as steepage of the UHPC concrete. So what's the resolution? And again, this problem we faced during the construction. And for future, the resolution is that use a snug-tight seal around the PEX sleeve and drill the hole with 1/16 smaller than the sleeve. Install the sleeve using a soft-headed hammer. Now, all this rod and straps, they were instrumented with the strain gauges, and then we have so many strain gauges. Some of them were damaged during the construction, and then issue faced a small clearance around this rod. So what we propose is that if we can install the strain gauges after, that will be better, or right now there are so many techniques that you can adopt as a non-contact structural monitoring system and using the digital image correlation technique, so no need for the strain gauges. Removal of the form used to shape the inter-girders, because we have to have the formwork for the slab. And this piece of wood was in between the two GFRP blocks, and we already had those horizontal and diagonal rods, so it was very difficult to remove it. Although if you keep it in place, it doesn't hurt. And then for future use of beveled formwork edge recommended, and so on. So the sequence of assembly also we found that could have been done in a different way because of the tight spacing and the precise detailing, as we have seen in all the components. And this required attention toward the construction sequence. Using of the box girder limited the point of entry for the insertion of the GFRP, as well to that concrete cast inside the box, and resolution, stage construction, placement of the cross bracing before inserting the horizontal straps. So we learned from all of this, and assembly of the inner girder followed by the outer girders. The final steel, that's the bottom view. You can see all the wiring coming from the one at the top left-hand side from the strain gauges, Okay, so I'm just going to show you what we did on the prototype test scale 1/4 shows here. So we tested this system under static load using the Canadian code, the 625 trucks. We load configuration. And we have, this shows the location where we put the truck. So we moved it around in the transfer direction and longitudinal directions. So we did concentric and eccentric load position. And we looked at the quasi-static load cycle according to the ACI 437 prototype, testing protocol. And we look at the surface and the ultimate condition. So one of the objectives was to assess the load distribution behavior and look at the overall performance of the system and its component. So 10 different configurations for the truck load on the girders, as you can see here. Again, I'm not going to go over the detail of the testing, but I'm just showing that after we finish all of this for service condition, we took the load all the way to failure. Mentioned that we adopted the regime based on the ACI 437, and there are certain regime for service load condition assessment, and then at the end all the way to the to failure. So in general, again, overall performance, that we were able to successfully incorporate this pseudo-ductility behavior in global behavior actually. The strong transverse composite action was achieved via the horizontal system, as well the vertical and diagonal cross bracing. We did achieve a consistent distribution of the forces between the adjacent girders. And then I would like to acknowledge all the support provided by several institutes, and I'll be more than happy to ask questions.
Thank you for the very interesting presentation. And I would like I would ask you if you could spend a few more words on this pseudo-ductility. How do you succeed in having such a ductility with brittle material? Thank you for this.
Okay. I've been mentioned that this pseudo-ductility is by allowing the progressive failure to happen in a consequence, and it was based on selecting the material based on the strain. So this CFRP has a lower strain, so that's how we incorporated that, what's called the pseudo-ductility term. So we forced the failure to happen by rupture of the FRP, not the GFRP box.
The construction of the GFRP tube, am I assuming that it's pultruded?
Yes.
And was there anything special, or was this off-the-shelf pultruded tube versus something that they would have done with specific stitch fabrics and something that's a little bit more robust?
Yeah, that's a good question. When we contacted the company, again, ACI won't allow us to say any word, any name. They said, okay, we're having right now some production. Will you take from this lineup? So that was the reason we used the pultruded. You can say what was available off the shelf. And they said in the future, if you need more, because we started this in 2005, and I said, we're not going to have the same. So right now, we still have in the lab about 12 beams that are 6 meters long. And Dr. Badri can support me in this.
Okay, because
so
it would take some special construction to do what you're doing,
yeah.
Which is why I asked the question. Yeah. And I assume it wasn't
the best. It wasn't the best type of construction for the GFRP.
So it wasn't optimized per se. It was just what was available, and I assume that it was a polyester resin that they had used.
Yes.
Yeah.
Yes. Yeah.